Hello friends, you are watching ERUDIRE PLUS, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, you know that Cyclone Separator plays a very important role in separating particulates from fluids in industry. Today in our analysis we'll show CFD flow solution and particle study through a Cyclone Separator. In this Cyclone Separator we are having one entry and two exit points, and from the entry we are providing different sizes particles at specific velocities. Some particles will be coming out from the down and some will be going out from the top. For better performance of the Cyclone Separator, we can provide one fan or motor at the top position. So this one also can be provided as input variables. We're having different types of input variables like inlet velocity or inlet mass flow rate, or we can say that velocity of the fan at the top position. In one of our previous videos, we have done a particle study and optimization based on the velocities of inlet particles. In this particle study, we will change the dimensions of the floor particles and see how much particles will be coming out from this down portion and how much particle will be going out from the top. And from this data, we'll try to optimize to have a desired value of particulates from the top and from the bottom also. Okay, done. So in this model, the lifts have already been provided at 3 different locations. We are having one entry and 2 exits, and for starting that CFD flow simulation we have to start with flow simulation, and the environment of CFD flow simulation will be initiated with wizard itself. We are starting from wizard and default project name we are keeping as project 2. Next to that we have to select that unit system. Unit system we are considering as SI. If you like, we can have a different unit system as per our wish. We can create here itself, but we're following standard SI system. And in this case, temperature we'll consider as degrees Celsius. And again, angular velocity of the fan we'll consider as RPM. That will come from load and motions. From here we will change the angular velocity as rotations per minute. Next, it is an internal analysis. We're excluding cavities without flow conditions. It is not a heat conduction in solid, so we will not consider this one. In this analysis, gravity is a very important part, and the direction of gravity is Y. So along Y it will be minus 9.81 meter per second square, and along Z component it will be 0. As we are providing one fan for better performance of this Cyclone Separator, so we have to consider rotation here. Next, gases it will be air only. And for particle study, material will be taken later on. Next, default wall thermal conditions and roughness values we are considering. Next, thermodynamic parameters. Temperature will be 20 degrees centigrade and pressure will be 101.325 Pascal. Let us finish this. This is the computational domain. Now we can hide this part and we can apply our boundary conditions. For applying initial conditions and boundary conditions, it is always suggested to have a segmented view of this model. So we can cut the model from front plane and apply boundary conditions in a better way. First of all, you have to provide the fan speed. It will be coming from rotating regions. Insert rotating region, and at the top location we have provided one fan that will be rotating with a speed of 1000 rpm, and minus sign is indicating that it will be moving with anti-clockwise direction. Green check. Next to that, you have to provide input variables from the entry location. So we can rotate this model a little bit. and we can cut this model across the plane containing that inlet entry location. We'll cut this one in a different way. Let's cut it and drag it along the plane from which the fluid particles will be entering. We've cut this one along front plane and we have dragged the plane little bit inside to make a proper selection of the inlet entry or fluid particles. Now we are applying boundary conditions from the entry locations. Let us select the boundary conditions, insert boundary condition, and for inlet location we can apply different things like inlet mass flow rate or inlet velocity. Let us consider the inlet velocity to be 60 meter per second. Selected. Next to that you have to apply two more boundary conditions at the exit locations. That will be atmospheric pressure at the exit locations. Again you have to cut the model in a different way to select the exit locations. You can drag it a little bit. Done. Boundary conditions, insert boundary condition. It will be atmospheric pressure at the exit locations. You can select the exit locations from here. One is selected. That is the exit at the bottom part. Now we have to select the exit at the top part also. We can select it. Done. Both the boundary conditions have been applied properly. Next to that we have to find out some goals. From the goals we want to find out surface goals. That means we want to have velocity at two different exit locations. Goals. Insert surface goals. Average velocity. Velocity at the top surface we have selected. Green check. Another goal to be defined, that means velocity at the bottom part also should be selected. We can rotate a little bit to have the bottom part. Goals. Insert surface goal. You have to have average velocity of fluid at the bottom part. Selected. Two goals we have defined. Now we can rename these things as velocity at top exit, and the second one we can rename as velocity at bottom exit. Both the goals have been defined. Now we can select the complete view of the model and let us see the isometric view of this one. Okay. Next to that we can have a beta mesh to have better results. Let us see global mesh and we can edit these things. And for editing we can have refinement of mesh. Select from manual and let us see the refinement. Display refinement level. You can see here the refinement level is only 1. So the mesh we have to modify. Let us modify up to 3 level of refinement. Green check. Done. Now we can run this. Solve with new calculations. Solver window has already started running. Mesh capturing is going on. Let us see the results from the solver window itself. We have defined 2 different goals. Let us see the values of these things. You can see that velocity at top exit is very high because at the top we have provided one fan to have better performance. Solver is finished. You can see at the top exit level velocity is 218.467 meter per second, and at the bottom exit it is 70.475 meter per second, and the inlet velocity was 60 meter per second. Okay, now first of all we'll see the results from the cut plots and other things. Next to that we will go for particle study with solid particles. Let us close these things. Results, and you want to see cut plots. Insert cut plots. You want to see from front plane, and from here you want to see velocity and pressure both separately. First of all, we'll see velocity of fluid particles. Green check. Let us see from front plane. We can have a view from front side. Let us play this. We can see the velocity of fluid particles through this cyclone separator. At different points we can see the different velocities. So at the true exit levels, velocity is very high, and in between the velocities, normal range is below 22.123 meter per second, and at the entry and exit points, velocity is high. Maximum velocity is observed at the top exit level. Okay, let us close this one, clear and hide. Next to that, you want to see the pressure distribution also. Edit definition, and you want to see pressure from front plane. Green check. Let us play these things, and throughout this cyclone separator, pressure is very high, and you can see low pressure at the top exit. By the same time, you can see bottom point also, it is a low pressure. Okay, so let us clear and hide these things. Cut plot 1, clear and hide. Next to that, we want to see some surface plots to have pressure distribution at different surfaces. Insert surface plots, and we want to select all faces. You want to see pressure only, because we know that velocity at the boundary will be 0. So we want to see pressure distribution at different surfaces. It is clearly visible that pressure at the top exit is very less. It is equal to atmospheric pressure, indicated by blue color, and bottom also it is high, but compared to the inner region it is less. Throughout this cyclone separator, pressure is very high, but at the top and bottom it is little less. Let us clear and hide these things. Clear and hide. Next to that, we want to show flow trajectories. We want to see the dynamics of flow particles through this cyclone separator. For seeing these things, we will cut this model from front plane. Instead of 20 numbers, we will select 100 numbers of particles, and we are going to see the particles in the form of arrows only. Arrows of diameter 0.03 meter. Let us select that bottom exit point, and also we have to select that top exit point also. We have selected phase 1 and phase 2, that means bottom exit and top exit. From these two surfaces, we'll see the flow particles will be moving out. Green check. Particle study is running. Let the study move on. Let us see the dynamics of flow particles from here. Let us play this. It is clearly visible that some particles are going out from the top exit, and some particles are moving out from the bottom exit also, right? The pressure at the top exit is minimum, indicating blue color. Some kind of circular motion is created inside this cyclone separator, and Here at this location, the separation of particulates are occurring, right? Next to that, we will move on to our most important part, that means particle study. And in particle study, we can have different input variables. In one of our previous videos, we have considered the inlet velocity as the input variable for optimization. In this case, we'll consider particle size as the input variable. Even rotation of the fan also can be considered as one of the input variables to see the variation of results. Okay, let us close these things, clear and hide. Next to that, we are moving to the most important part of our analysis, that means particle study. We are starting particle study from here, and it will be initiated with wizard. We are keeping the default name of this study as particle study 1. Next, instead of 20 numbers of particles, we'll keep this one as 100 numbers to have a better representation of these flow particles. Instead of liquids, you can select this one as solids, and the diameters of these flow particles is 0.0001. We can vary these things. Let us make this particle size very small, right? Let us make these particles as 0.401 meter. In this particle study, we are considering iron particles of diameter 10 to the minus 5 meter and with a mass flow rate of 1 kg per second. We have to select that location from which the particles will be initiated. Let us select that entry position, select other, it is lead number 1, that is phase 1 selected. From phase 1, 100 numbers of iron particles with diameter 10 to the minus 5 meter with a mass flow rate of 1 kg per second, it will be initiated from the entry location. Next, as some particles will be accumulated at the bottom exit point, so definitely it will be accretion and erosion effect will be also working in this case. Next to that, you can see the surface wall conditions. As we are injecting solid iron particles, so it will not be accumulated at the surface walls. It will be suffering ideal reflection. Next to that, we can see trajectories and statistics as our post-processing results. Finally, we can run this particle study. Particle study is running. Now we have to play the injection. Let us play this injection. You can see from front side, you can see here some particles are moving out and some particles are accumulated at the bottom exit points, right? From the surface parameters, we can identify how many particles are accumulated at the bottom exit and how many particles are going out from the top locations, right? Next to that, we want to move on to surface parameters. Insert surface parameters, and we can find out all the parameters like density, mass flow rate, pressure, etc. at any location. In our task at this moment, we want to find out the numbers of particles to be accumulated at the bottommost location. So we can select the numbers of particles from here. Even mass accumulation rate, erosion number, total numbers of accumulation rate, etc. We can find out all the thick parameters, right? We don't want to see all these parameters. By viewing these dynamics of flow particles, we can identify that some numbers of particles are accumulated at the bottommost part and some particles are going out from the top exit locations. We have to see surface parameters at any location. Suppose we want to see surface parameter at the bottommost part, right? So what we'll do is rotate view, select other, and lead number 3 is selected, and we want to see the numbers of particles to be accumulated at the bottommost part, even mass erosion rate, mass accumulation rate, erosion rate, etc. We can select everything. Let us select all and show. So we are having a lot of parameters like pressure, density, velocity, x, y, z directions. By the same time, numbers of particles to be accumulated at the bottommost part. You can see numbers of particles to be accumulated at the bottommost part is 11. And also we can see total accumulation rate is 0.0821 kg per second. It is very less because only 11 particles are being accumulated at the bottommost part. And maximum particles are going out. That means 89 numbers of particles are moving out from the top exit, right? Next to that, we'll change the diameter of this input variable and see the behavior. Okay, so let us close these things. Let us hide this part, and we have to go for different particle study. We can clear and hide this one. Let us hide this injection. Next to that, we want to go for another particle study with different diameter. So, particle studies, and we can start with wizard. Default name of the study as particle study 2. Next, instead of 20 numbers, we'll make it 100 as before. And the particle diameter, in this case it will be a little bit more. Let us select the number to be 0.201 meter, and instead of liquids we want to select this one as solids, and we will be considering iron particles of diameter 0.201 meter. Mass flow rate, it will be same like before, it will be 1 kg per second, and initial particle velocity and initial particle temperature we are not considering. Okay, we have to select that location from which the flow particles will be initiated. Let us select that location, select other. This is lead number 1 selected. Next to that, we have to select both erosion and accretion. Next, it will be ideal reflections at the wall. Next, we have to see trajectories and statistics as a post-processing part. Let us run this one. Particle study 2 is running. It is done. Now we can see the injection and we can play it. Particle study 2, it is clearly visible that as the diameter in this case is more, so maximum particles are being accumulated at the bottommost part and few particles are going out from the top exit. You can see this one from front plane in a better way. You can see clearly as the diameter in this case is very high compared to the previous one, so fewer particles are being exiting from the top surface and maximum particles are being accumulated at the bottommost part, right? You can see these things from surface parameters also. Let us select the surface parameters from that bottom exit point. So we can rotate this little bit. surface parameters, insert surface parameters, and I'm going to select that bottommost part, select other, lid number 3 is selected, this phase 1, and from here we can select all the parameters. Let us show. Now compared to the previous one, in this case more numbers of particles are being accumulated at the bottommost part. You can see 23 numbers of particles are accumulated, and other parameters you can see mass accumulated rate is very high in this case compared to previous one. It is 0.1733 kg per second, and pressure, density, etc. all the parameters we can see from here, right? So from these parameters we can have better representation of all this data using Excel. We can transport all this data to Excel and have a better representation of all these results. Now instead of stopping it here, we can go for different dimensions of these input variables, and with these dimensions we can have a comparative study of all these results. Okay, so this is all about our today's CFD flow simulation and particle study of a cyclone separator using SolidWorks. Okay, if you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.